So welcome back. This is our last regular Friday class that we'll host for CSC 241. It's 18 November. A week from today, it will be Black Friday. Woohoo! The day after Thanksgiving. All of us will be stuffed with turkey or something at that point. Who knows? We have a couple of quick concepts to finish in our Module 5 study guide. We don't have as many student learning objectives, but there's plenty of content, less to read in the book, more to read and cover in the study guide and addendum, some additional references. I am considering extending the student learning objectives from Module 6, which are special topics, as opposed to having two separate assessments, but I'll make that decision later today, and then if there is a change, I will send notice that we're folding the content from Module 6 into Module 5. I don't think so, though. What I'd like to do is finish the review here, put the assessment out, let you get a first attempt over the weekend, and then wrap up Module 6 in a single session, what remains of Module 6. We were in page 15, and one of the things that we wanted to call out was this idea of what's known as a mean time between failure. So how much do people spend on a hard disk if they go to Office Max? Or if you get a hard disk in a place like, if you could get it from Kmart and so on, what would you pay today? Anyone?
What I remember seeing it for like $68 or something.
Right, $68, and that's a little high because we're paying to ship it to the islands here, but essentially hard disks were very expensive. About 35 years ago, they were $2,500, and basically they held just 10 megabytes of data, but they were still quite the advance, right? So they were still quite an advancement over floppy disks. What's inside the enclosure here is usually inert gases like helium, the kinds of stuff you put in birthday balloons or celebration balloons. And that reduces the incidence of corrosion, and it extends the life of traditional hard disks. So this acronym, mean time between failure, that's the amount of hours of operation you can expect from a traditional hard drive, where you typically get 1 million hours of operation before it fails on average. Now, if I take 1 million and I divide that by 24 in a day and divide that by 365, in theory, my hard drives should last 114 years on average. So why is there a difference? Well, there are differences in power quality, differences in environmental conditions. Some hard drives are in laptops and mobile systems are knocked around a good bit. So what happens is that this all chips down, right? So if we basically take 1 million and divide by the number of hours in a year, 365 times 24, we get 8,760 hours in a year in theory. What did we say was 30% of the hardware failure, a source of failure for 30% of hardware failures? What have we already told you earlier in this class? It accounts for, go ahead.
Improper grounding.
Improper grounding, which has to do with the quality of electricity, right? So in some places, that's a much higher factor. That's an average also. 30% is an average also. So in some areas, it's a lot higher than 30%. Now, there are other innovations that have been implemented in different generations of hard disks to improve the capacity and reliability. They use thinner platters. They use motors to spin the platters. These are like basically like CD or DVD discs, Blu-ray discs, right? So, except they're metal and they spin. So here you see earlier models that used air with 5 discs. And then here you see with helium 7 discs. You get a lot greater capacity. You get much longer life. And so this is just one aspect of innovation for traditional hard drives that has extended their wear and tear. Each one of these heads is like a record needle, and anytime you knock the disk around, it scratches the head. So that's one thing to remember. Another speed enhancement that's common for traditional disks is something called redundant array of inexpensive disks, or RAID. You can pair or work disks in tandem as a team. So it's like interleaving with memory. And if you're a speed junkie, you can spring for extra and replace or purchase disks that use solid state memory modules instead of, these are flash memory modules made out of NAND. We've already talked about USB and SSDs, and basically you can use those with RAID to even to increase even that much more. So you can get 2, 3, 5, 10 times the speed for traditional hard disks by pairing them up and using them in tandem as a team with different types of RAID. We'll talk more about that later. You can also double the speed of your disk access by using solid state hard drives. And if you use solid state hard drives with RAID, then it could be 10, 20 times faster in terms of disk access. So the latest hard disks actually use a smaller SSD drive on the front of the disk. So they put solid state components on the front, and that's what they use to start the computer up, and then the rest of the system data and applications is stored in a traditional thing. So it's common to see a lot of hybrid disks. When you have a hybrid disk, it kind of changes the whole memory continuum, because remember, memory gets faster and cheaper and larger the further down the table that you work. But if you get to a traditional hard disk that has a solid state component built in, it kind of wrinkles that table a little bit, so that you'd have at the end of this, everybody know what I'm talking about? The end of this table right here, at the end of this table or this diagram right here, you have virtual memory. That's hard disk memory. You could have like a second component down here where you have hybrid disks or SSD disks, and then you have traditional hard disks, right? So you'd have to have another space in here. Now there is a new innovation called Optane, which basically creates memory that works like RAM and hard disk. Optane, or 3D XPoint, it's spelled XPoint. It's a new innovation that's been around about 4 or 5 years at this point. First came out in data centers, and it's now available in a lot of high-end gaming laptops and such. Optane basically has the benefits of both RAM and hard disk solid state drives. So there could be some significant innovations in operating system design, and in terms of the von Neumann diagram, where the whole right left half of the diagram is no longer necessary. Nobody has actually rebuilt or redesigned the way that the computer model operates since Optane and 3D XPoint have come onto the scene. And I think what's happening is that a lot of operating system engineers and designers, as well as Hardware designers are trying to figure out, okay, if we have something that works like RAM and it works like a hard disk, how could our von Neumann diagram be differently? To date, nobody has really stretched the envelope that way. They just use it as a really fast hard drive, right? So it has the benefits of RAM. It's almost as fast as RAM, but it's the same as a solid state hard drive. And that's what they're doing with Optane to this point. Optane and 3D XPoint, we just talked about. Those special developments that have happened are basically the brainchild of two major corporations, Intel and Micron. It's a kind of a partnership between Intel and Micron. Micron manufactures RAM. So, moving back to this, let's talk about external disks and network maps or network drives, right? So you can take the memory table and you can keep adding more rows to the memory table. I can take my file explorer, and if I'm connected on a network and there's a server and the server has fast RAID hard disks, I can basically select the name of my computer here. Watch what happens to the menus and the options up here. Everyone watch what happens when I select the name of my computer. Everybody see what happened there up here? Right? So you can add network disks. You hit the pull down and you can map a network drive. Essentially, a network server can share a directory or an entire disk. And if they share it, there's a good way to do it and a very bad way to do it. You should always share it with a $sign. I can do this with my own laptop. I can basically take a temp folder or any folder. Let's say I wanted to share my temp folder on my home network. I can essentially go to Properties. With the right mouse click, I can select Sharing. I don't want to use this wizard button. That's a terrible way to go. Everybody should be using the advanced sharing. You can click on advanced sharing and share this folder on the network. And the folder name is going to be, part of that name is going to be the name of my computer, which is ThinkPad1, and the name of the folder. Now I can change the share name, but the most important thing I need to do, and this is critical. Everybody needs to pay attention here. You need everybody to stop what you're doing. If you're multitasking, lean in close. You don't want to miss this. If you share it like this, it's visible to everybody on your network. That means everybody can get in your Kool-Aid. Whether you set permissions or not, they can get at it because it's an attractive nuisance. You want to add a $sign to the end of the share name. By adding a $sign to the end of the share name on a network drive, I am setting up a network drive. I am using my temp directory to create a network drive that anyone in my home network can connect to just because they're on the network. But I'm going to share it with the name that ends with a $sign character. When I hit this and say OK, I can also basically go into security. So in advanced sharing, I can set up share permissions, which are network-based permissions. And then in addition, a best practice is to also set up security permissions and privileges using the file system on the local disk, so that I have two layers of permissions defined. If I do not define share permissions on the network this way, which are going to look a little differently than file system, I can have full control, change permissions, or read permissions, right? Across the network, those permissions are pretty simple, and they've been around a long time. In Windows 7 and higher, actually Windows XP and higher, for a long time, NTFS has been the new technology file system. NTFS is the file system that Windows uses. When I am finished establishing my share permissions on the network, I can also establish local permissions on the hard disk for the temp directory. When I do this, I should click into the advanced options. A lot of people click right here and go into edit. And if you do that, there's a lot of things you don't get a chance to define. I like using the advanced option. And there you can add the names of people. You can define whether they have modified privileges, which is different than a network share. A network share has change permissions. File system permissions are modify, right? Full control is still full control. If I change that, I can change it to read write as opposed to just read. So if I see read write, that's a file system permission. And unless the name of the account that's accessing it locally on that disk is in this listing, they can't get on here. So you can have a case where somebody can get to it across the network with the share permissions, but if you also establish the security permissions on the disk itself, you can prevent unauthorized access, okay? It is a best practice to configure both. In any case, many people are not aware of how easy it is to share, just to share a folder and then surprise, everybody can see it, right? That's a network. That's what we mean by a network drive map. You map to a drive letter. So once I have this shared, I can go into another machine and I can point to ThinkPad 1 with a command and I can connect to this. Now, how do I connect to something like that? Well, I map to a network drive. I'm going to do something that doesn't make any sense. I'm going to connect to myself just to show you how it works. So I can pick the drive letter. Let's say I'm going to choose drive letter T for temp, right? Because I know I'm going to connect to a temp directory. Now let's pretend that my ThinkPad is actually a server. I'm going to use what's called a UNC, a Universal Naming Convention, right? It's kind of like a web address. I'm going to put in ThinkPad 1, or I could put in the IP address. Right? I could put in the IP address of a system. So I can also go by IP addresses. And then I'm going to put another backslash, and I'll go ahead and put temp $. When I click finish, it's going to create a T drive. So when I look at my ThinkPad now, oh, look, if we were pretending this was a server, now I have a C drive and I have a network drive called drive letter T. It's pretty cool stuff. Now I can just click on this and then right click on it and then disconnect it. Right? It says, oh, you currently have files open. Well, yeah, because I had a screen open. Yeah. Any questions about what we mean by drive maps? Now, this is a really cool thing. You can use a USB flash. You can use USB flash memory or a USB hard drive, right? A thumb drive. You can put the entire operating system on a USB drive and you can boot the entire system from that thumb drive. It's not as fast as booting from a hard disk, but if you need to be able to get onto a system where the hard drive has crashed, you can still recover memory by putting an operating system on a USB drive, plugging it in, going into the BIOS, and changing the boot order so that you boot first from a USB instead of from the CD or DVD. Is there anyone that has any questions about this kind of thing? You should watch these links. That's really cool. There's a version of Linux called Sugar on a Stick. I want to see if this is actually still pulling properly. Yep.
For just $67.
Okay.
As many videos as you want.
Yeah, we're not going to watch the commercial. But I did want to cue you into this. Now there is a way where you can take the fast memory which is dual ported on your graphics card, and you can use it to reinvent or kind of repurpose, rewire, if you will. It's not technically rewiring, but you can use that fast shared memory, dual ported memory, and the graphics processor in your graphics card, and you can use that to create a hugely powerful CPU, something that adds to the CPU, does floating point. And you can use it as a supercomputer. Put another way, you can take your gaming system, and if you add another graphics card to it and stitch the two together, you can create a very low cost but yet very powerful supercomputer. And that's something that's kind of a cutting edge new thing that is much like the Optane or 3DX point. Any questions? So if a USB is really just another hard drive loading Windows or Linux, are there other disks a computer can access that might work the same way? So the answer is yes. You can also use a shared directory on the network. And if it's shared in a special way using a protocol that's known as iSCSI, you can use a network connection, and basically what happens is that that network drive can be used to boot the system. What am I saying? I'm saying that you don't have to have a hard disk to boot a system. You can connect across a network for a special kind of drive map, and when you create a SAN, it's called a storage area network, using iSCSI, essentially your Ethernet connection is like a hard disk cable. Let's repeat that. When you use network storage and configure it in a special way to create a storage area network using a protocol, a network protocol called iSCSI, it turns your network cable into like a very long hard disk cable. And you can boot your system from a network disk instead of using, now the logical unit number, or LUN, is how your system can tap this. And if you have a version of Windows 10 or 11 that's the professional edition or higher, if you have Windows 10 or Windows 11 Professional Edition, you can go into the administrative tools, and there is actually a utility called the iSCSI Initiator, and you can connect to these network drives so that they're always connected, and you can configure this. And then if it's a bootable disk, you can remove your C drive and just boot from there. So what are we saying? You can have lots of servers in a very small box because they're diskless. They don't need hard drives. Okay, let me repeat that. With this innovation, you can create lots of computer hardware. You can have multiple servers in a single box. It's called a blade server. And a blade server has a bunch of big cards, kind of like graphics controllers, and those cards have a CPU and memory. They don't have a disk. Each one of the cards is a full-blown server. And a single chassis in a data center can house a dozen servers, a dozen very large, very powerful servers, and they connect to the storage area network across the network. And those network Ethernet cables and cards are bound together in something called Ether channel, so that you get 4, 6, 10, 12 gigabits of performance between that machine and your storage area network. And why would you do that? Well, it's a way of getting a whole lot more into a much smaller place, right? So for types and criteria of memory, here's what we have so far. You have chip-based memory, you have system RAM, you have internal disk memory, you have external disk memory, and then you have cloud disk memory. Now, as you go from one to the other, it's like 100-fold decrease in speed. We call that a 2 order of magnitude. An order of magnitude is 10 times, right? So when something is an order of magnitude more or less, it's either 1/10 or 10 times, depending on which direction you're moving. Any questions about what an order of magnitude means? If you have an order of magnitude and an order of magnitude together, it's 100 times difference. How many of you have heard of the Richter scale for earthquakes? Anybody?
Yeah.
Okay. Did you know that the Richter scale, an earthquake that has, it's an earthquake with, it's a rated 6. It's a 6 on the Richter scale. That's 10 times as powerful as an earthquake that has a 5 rating on the Richter scale, right? So if it's an if it's an earthquake that's a 6 point, it's like a 6.0, it's 10 times worse in terms of the destructive energy than one that's 5.0, which is why 6 is a big deal. Okay, is everybody still with me? Are we there? Did I lose anyone? Can you unmute? We just had a power cut over. Hello, hello? Can anyone unmute? Hello, hello?
Hello.
Are we back? Do we have everybody?
Yeah, it was just you who's left.
Yeah, the power cut back on here on island. So we were talking about the different factors of capacity, right? And speed. So it's 100, it's 2 orders of magnitude slower as you move further away when you get to cloud memory. So if it's 100 times slower going from chip-based, it's 100 times slower going from the level 1 cache and registers on the CPU to RAM, okay? So if you go from the register CPU to L3 cache, that's 100 times slower than what's happening on the register. And then when you go from the L3 cache to system RAM, that's 100 times slower. And then when you go from RAM to the internal hard drive, that's 100 times slower. And when you go to a network drive, that's 100 times slower than a hard disk, right? So it's 100 times slower than the type of memory before, but it's also larger and larger and larger. Cloud-based disk memory is 100 times slower than a local network drive. So you can have a local network with a shared directory. In your home, you can have like a media network where you share all your media and music and movies and stuff. You have a media center and it's tied into your wireless. But if you go to put stuff out in the cloud, it's 100 times slower beyond the local network. The thing to remember is that by the time you finish going like 100 and then another 100 and another 100, you're dealing with many orders of magnitude slower. And so the goal is to keep getting the data you use the most often closest to the CPU. That's the trick. OneDrive, Google Drive, iCloud, Dropbox, that's 100 times slower than a USB thumb drive, right? Or a network drive, right? And those are 100 times slower than a local disk. Any questions about how that works? Anybody? I have another person on the roster, I think. If I look, oh yeah, I'm gonna update. So can somebody unmute just so I'm sure you're with us still?
Yep.
Okay, thank you. So this is where I
Mhm.
talked about the 3DX point or Optane memory and how it's sort of it's a combination or fusion of RAM and solid state hard drive, right? So it has the advantages of both. There's some information there. It's really important to understand that. What I'd like to do with our remaining time is make sure we cover the information that we need to cover about the types of different chips. So when you're creating a CPU, you have to create instruction sets to work with those CPUs. You have to have something called assembly language so that an operating system can make calls to the hardware. So this is one thing that's important to understand about hardware and computer architecture. When you're talking about a CPU, there's other components that have to be a part of that development. And what's most important to understand is that when you have a complex, when you have a CPU that's designed to support a wide range of computing interests, like an Intel processor or an AMD processor, these have been traditionally designed with instruction sets and assembly language and system calls, low-level system calls, so that basically you can use a PC or a laptop for all sorts of things, a wide range of interests, right? And what happens is that because you have a general purpose CPU, you have to have all kinds of extra functions built into the instruction set, all kinds of extra resources built in to the assembly language. And the operating system that uses them can only be fine-tuned to a certain point. It's a general purpose operating system. Over the years, what's happened is that this has become kind of like a bottleneck. And what they've discovered is that if they redesign the CPU so that it has fewer instructions, it's called a reduced instruction set computing processor or CPU. A RISC CPU, and you may have heard of these, they come by different names. You can get ASICs that basically use reduced instruction sets. Those are special purpose, application specific integrated circuits, right? So there are subsets of the RISC genre. You may have heard of ARM, right? You have all sorts of special purpose processors. Some processors can be used even for music or audio processing, video processing. They're called DACs, digital to analog converters, DSPs. I'm oversimplifying here, but the point is that we can design a processor that's so specialized based on the kind of digital information that it engages. And if we supplement the design of our computer with a few specialized processors like DACs and analog to digital controllers, ACDs, or digital signal processors, there is less that the CISC CPU has to perform. So there's a huge gain in efficiency, okay? Now, we've talked about field programmable gate arrays before. This is like the liquid metal kind of thing, where ASICs are special purpose chips that are hardwired. They devised one that's flexible, where you can change the logic gates and how they are arranged. FPGAs were smaller, but now they're much larger and more complex. So Microsoft started using FPGAs as the lead processor for the machines they use for their data centers. So they can basically just rewrite the logic gate designs, instead of having to take out the hardwired CPUs. And Google, on the other hand, spent all kinds of money to hardwire specialized processors for their data centers because, well, it has a lot to do with their search engine, okay? The thing to remember is that in some cases, CPUs have become more specialized with reduced instruction computing, and especially mobile processors. Mobile processors like the Apple A7 processor or A8 processor. I don't know. They're probably much higher now. I don't know. What's the latest iPhone? It's like an A9, A10. They keep coming up. Those are ARM processors. Those are reduced instruction set. They're designed to work with lower voltage. They're designed to work better with mobile. They're not designed to run in a general computing environment, right? So there's more information here about the RISC architecture and about how processors can be multi-threaded or hyper-threaded to increase the performance, where the physical cores of the processor are virtualized into 2 or more processors, right? So that's what we mean by hyper-threading. Here is a comparison of the number of cores for a CISC processor like an Intel i5. Can everybody see this?
Yeah.
Yeah.
And this is an example of the cores you would find in a graphics controller used for gaming or for high performance computing. Each of these cores is much smaller. There's a reduced instruction set, but they're very, very good at floating point calculations, the kinds of things that involve decimal points. Floating point meaning decimal points, large numbers for graphics, for supercomputing, and so on. That's why you can build a supercomputer with a machine that you add graphics controllers to, right? So the cores of a GPU are designed with many high performance FPUs or floating point units, right? Those cores. And so this is like your Intel i7 or i5 processor, and it's general purpose computing, and this would be specialized for graphics. You can take advantage of this convention. In fact, if you have a graphics controller in Windows and you use the right software, you can now right-click something and there will be a run with the GPU option where it'll compute and run with the graphics controller instead of the CPU. And you get much better performance. So that's something that's new in latest versions of Windows 10, right? The whole idea of having extra threads or using virtual multiples of a hardware core has been around a long time. So CPU designs also incorporate this multi-threading or hyper-threading. For consumer CPUs, you normally double the number of cores, and for most standard server CPUs. But for special high-end supercomputers, the multiples can be as high as 6 or 10 or 12 cores, virtual cores for every physical core. This last piece we've already talked about. We've told you about how when your computer is powered on, the operating system takes memory addresses and it creates a virtual representation of each of the hardware components. So this is just a recap of that same thing, right? What I'd like you to do is go ahead and just take a quick look at how some of these hardware designs have been evolved, how they've been developed over the years. There's an organization of electrical engineers and computer engineers, right? The International Engineering Task Force and the IEEE, and so there are some links. When people are designing these hardware standards, they put out a request for comments about, hey, how do we have better USB drives? How do we work faster graphics cards? How do we change our Wi-Fi so we have Wi-Fi 6 and it's quicker? That's what this is all about right here. I wanted to point this out to you. And then, of course, virtual memory, right? Virtual machines. You can create a machine within a machine This is something we've already talked about and reviewed before. I just didn't want you to forget about it. So we're at the end of our study guide for Module 5. I will put the first version of your Module 5 assessment out there on Blackboard. Please see if you can do what you can to complete your first attempt of the Module 5 assessment by the time we start class on Monday. And I'll have a short assignment for you in Module 5. We'll have a final solution in Module 6. So one assignment, one solution. The assignment in Module 5, short thing to do to help with this, with the content here. And then in Module 6, early next week, you'll do one thing for a solution as we begin Module 6. Any questions about where we are and what comes next?